This call is now being recorded.
Hello everyone, thanks for being with us today. The speaker today is Vlad Tkachuk. He's a second-year PhD student in computing science at University of Alberta, working with Csaba Csepesvári and Chaoki Tan. He completed his master degree also at University of Alberta with Csaba Csepesvári. And before that, he obtained his bachelor in electrical engineering at the University of Waterloo. Is especially interested in reinforcement learning theory, and today we'll talk about offline reinforcement learning in the challenging setting of a linear qπ-Realizable MDP. Thanks a lot for accepting our invitation, and the stage is yours. Thank you.
Great. Okay. Thank you, everyone. So today I'm going to talk about this paper from NeurIPS 2024. And the title, I guess, kind of explains the whole thing, which is like, we show that this trajectory data is going to suffice for statistically efficient learning in this offline RL setting, where you have the added assumptions of linear qπ-Realizability and something called Concentrability. And this is joint work with Gellert and Csaba from DeepMind. Okay, so I start with like the obligatory slide of motivating this work. So why care about offline data? Well, I guess like one thing is there's a lot of settings where safety concerns are a thing, and you might not want to act online. And like, as we have seen with a lot of these language models, there's a ton of offline data that can be used in a very like effective way. And if you ask ChatGPT, it seems to kind of align with what I said, which is like, yeah, there's all these safety critical and risk settings that offline data is useful for. Okay, and I'm going to start the talk actually with just a really quick summary of what's going to like what the whole talk is about, and then we'll get into all the details. Okay, so the summary is as follows. So what I first explained to you is kind of like what we knew prior to this paper, and then the next thing that appears is what we did. Okay, so the setting we care about is this offline RL setting, and we're going to specifically care about the finite horizon setting. The two assumptions we're going to have here is this thing called qπ-Realizability. This means that all the qπ functions, so for all policies, they're linear in some set of known features. And there's a second assumption called concentrability, which essentially says that the offline data covers the state and action space well based on any policy. Okay, and the objective we have here is something like design a sample efficient learner that outputs a near optimal policy. And sample efficient means like something like polynomial samples in the quantities we care about. So what was known was the following, which is this a negative result, and it's actually by Dylan, which is like efficient learning is not possible in the sense that the offline data set will have to depend on the state space size. So the size of the offline data set will have to scale with the state space size, and this is like not something we want to happen. Okay, and so in this work, what I'm basically going to show is that it is actually possible to do efficient learning with like one added assumption, and that added assumption is that this offline data is actually has like a special structure, which is it comes in full length trajectories. Okay, and now we begin with the like kind of long story of defining things and showing how this works. Okay, so the overview is like this, and the first kind of half of this presentation is actually based on like a more high level talk I gave at the University of Alberta, and then the second half is going to be like going over proof details, which is this like R method part of things. Okay, so let's begin, and I maybe will go through this a little bit quicker since I think most of the audience knows a lot of these details. Okay, so first of all, it's like defining the setting. Okay, so we work with MDPs, so finite horizon MDPs. So there's a horizon. The state space is going to have this like special layered structure, and this is without loss of much generality. But basically, at each stage at each stage H, there's like kind of the separate state space S subscript H that we're going to use. Okay. The action space is just some set of finite actions. We have these transition function, which is a map from like a state at stage H and action to your next state. We have a reward function, and for the purposes of this talk, it's going to be deterministic, but in the paper, it's stochastic and everything works. And we have a horizon, as I said, and then there's going to be an initial start state. Okay. So just like high level, we've seen this kind of stuff like this is an example of an MDP. And really the thing I just wanted to highlight is what this like finite horizon thing maybe looks like. So here you have 2 actions. Horizon, if we say the horizon is 3, that would mean that like after 3 steps of interacting with the MDP, you stop. So for instance, if the start state is S1, then you have these like layered state structure like this, where S1 is the states available at stage 1, S2 and S2 prime is kind of like the states available at stage 2, and then S3 is the state available at stage 3. And then there's like rewards that we label here, and the transition tells you how you move between states. Okay, I just wanted to point out this MDP because it'll come up a little bit later when we point out what trajectory data kind of looks like. And then the way that the agent is going to behave, and I'll explain like why we care about agents in a moment, but like an agent's going to have a behavior, and that's defined by something called a policy, and that's just a map from each state to some distribution of our actions. Okay, and the usual like interaction you see between MDP and agent is called this online RL setting, which is not what we consider, but just like I briefly mentioned, is like you have this agent, it takes an action, and then the MDP returns some like state and reward, and this repeatedly keeps on occurring. And the important thing is you have this like online interaction where you get to choose your actions. So the setting we consider is not this setting, and instead we actually have a bunch of offline data. So it's a bunch of like interactions with this MDP that have already occurred. Okay, and so yeah, we're gonna have it of this form. So like we're gonna have some data set of size n, and the main thing to note is that subscripts in this data set are the stages. So, and then the superscripts are the data indices. So here you have like n interactions from stage 1 to stage h. Okay, and the important thing is that here this is just like some general data in the sense that that the next state does not equal to the start state in these tuples. So like, I don't know if you can see my mouse, but this next state here would not equal to the following start state. Okay, so there's like no kind of connection between these tuples here. Okay, and so this is not trajectory data yet. This is just general offline data. Okay, and so like an example might be you have like one, if n is equal to 1, then you would have like something like this. Notice how S2 does not have to equal S2 prime here. And so the problem we like care about or are trying to solve more formally is the following. So first we should define what a value function is. And like a state value function would just be the cumulative expected reward that you get when following some policy pi from some state SH. And then we have something called an action value function, which is like the same thing as the action or the state value function, except it's if you start from state S and take action A. Okay. And there's something called an optimal policy, which is just a policy that achieves the maximum state value from the start state S1. Okay. And the objective will look something like this, which is like for any epsilon and delta with access to offline data of size polynomial and all the quantities of interest, and I'll address this state and action part in a second, you want to find a policy pi such that it's good, and good means it's epsilon close to the optimal policy in value with high probability. Okay, so of course you might notice immediately that the state and action space are very like unideal to have because they're very, very large. For example, things like chess and robotics. So we're just going to say that this is not acceptable, and we're going to say we really want the samples to scale polynomially in quantities independent of the state and action space. And we're going to like later on add some kind of complexity measure or like dimension of interest, but for now this is what we'll say. So this is kind of like the problem we care about. Is there any like questions about this before I move on to some results? Okay. So now I explain kind of like the background of what we know and like what's the kind of missing cell of the table that this work fills in. Okay, so I like to think of the stuff like high level as like there's a bunch of assumptions you're making, and then we try to understand under which assumptions things work. So like there's kind of like 2 main places we can make assumptions here, which is on like the type of data you have and the type of MDP you're working with. And like kind of like the holy grail would be to get something that works for like no assumptions on data and no assumptions on MDP. And so that would look something like if you had this table, like for all MDPs and for all data distributions, things just work. And like unsurprisingly, this is like not possible just for like the really simple case where if you just don't have data from a very informative state in action, say there's only one state in action that gives you reward 1, you're kind of hopeless. Okay. So this like inspires the first step, which is like, what assumptions should we make? And here we start with like this standard assumption that was already known, which is like concentrability. And roughly speaking, this just means good coverage of all the states and actions. Okay, so let's formally define that. So what that means is like, first, we're going to assume there's some distribution that generates states and actions. That's this mu of h. We'll call it the data gathering distribution. That generates every state and action for each stage. And then afterwards, you get the reward and next state based on the MDP structure. Okay. And then this concentrability assumption, okay, so there's like a picture of this. It just means the state and actions come from some distribution. And the concentrability assumption looks something like this, which is that it's going to say that like if you compare this data gathering distribution, which is the denominator, okay, to the marginal distribution of a state in action for any policy, that ratio is not too large. Or in other words, mu h, which is this data gathering distribution, gathers data as well as any policy. Okay. Okay, so this is like a fairly standard assumption. Okay, so like we kind of like ask what's going to happen here, and like just for the sake of time, it turns out like things don't work with just concentrability if you want independence of state and actions. So we're going to have to add like another kind of common assumption that people would want to make here, which is some way of like compressing the state and action space. And here, this is going to be some structure on the MDP, let's say. And so like a common one studied here is this idea of linear qπ-Realizability. And this is just roughly speaking is like value functions can be approximated linearly with respect to some features. Okay. And formally, that just means that we have some feature map that maps from states and actions to d-dimensional real numbers. And the assumption is going to be that this qπ function, so this is the function for a policy over states and actions, is linear in some features phi. Okay, so there exists some parameter theta pi h such that qπ is linear. So qπ is linear in these features. Okay, and so the problem or like the objective is going to change to something like, can we achieve this outputting this good policy under these assumptions of qπ-Realizability, concentrability, and we're going to be okay with the data scaling with the dimension d of the features and this concentrability coefficient c now. Okay, and so as I mentioned kind of in the summary, the result here is that things don't work, and this was the result of Dylan from 2021 here. Okay, so like at this point, the natural question to ask is like, well, like what are kind of maybe like sufficient conditions for things to work here? Okay, and there's like two directions you can kind of take here. So first I mentioned one direction that's not this work, but another work has taken, and it'll be useful for understanding what kind of like what we did. So that direction is like make stronger assumptions on the MDP or make different, let's say like different assumptions than linear qπ-Realizability. And one choice here is, oh, okay, so this is like the formal statement of the result. I'm not going to, but the main thing is like the data set will need to depend on S. Okay, right. So getting back to the story here is that, yeah, so like you can choose to make a stronger assumption kind of like on data or on the MDP. And first, we're going to look at what happens when you make a different assumption on MDPs. And like one choice here is to make this linear MDP assumption. This turns out to be a stronger assumption than linear qπ. And roughly speaking, it means something like transition and reward functions are linearly representable, or we're going to approximate them. Okay. Formally, the assumption looks like this, which says that the reward function R is a linear function of the features in terms of exists some parameter, and that the transitions are also a linear function for every next state S prime. So there's a parameter for every S prime that can linearly represent the transition as a function of phi. Okay, this turns out to be a stronger assumption than this qπ-Realizability. Okay, in the sense that every linear MDP is a qπ-realizable MDP, but not the other way around. And okay, so people have studied this setting, and the results are as follows, which is like you get positive results. Okay, so it turns out things work in this setting, and this like, yeah, this is a work by Non and others that show things will work with this linear MDP set. Okay, so kind of like the natural next. Okay, one thing to note is this thing I mentioned about the linear MDP is actually a slightly stronger assumption than what's needed. really all you need is something called Bellman completeness, which is not like a stronger assumption than linear qπ, is just like a different assumption. But for the purpose of this talk, the linear MDP structure will actually be kind of the important thing that we end up comparing qπ to, so I thought I'd mention it like this. Okay, so point is linear MDPs, things work. So the natural question to ask is like, if you didn't want to add extra like structural assumptions kind of to the MDP, if you didn't want to change the linear qπ assumption, can you do something, can you change the assumptions on the data to get things to kind of work here? Okay, and so that's what we explored in this paper, right? So we said, like, can we make some stronger assumption than concentrability? And I will mention there is other papers that make like stronger assumptions as well, and things do work. However, they are quite a bit stronger than what we claim we're making here, which is we're going to make the assumption of you still have concentrability, but the data just has the structure of being trajectory data. There's like another paper from a few years ago that changes this definition of concentrability to be something stronger as well. Okay, so yeah, so the table kind of looks like this now, which is like, okay, so we're going to want to fill in these question marks in the table here with this extra assumption. And now I explain what the assumption is and slightly motivated. So first, motivation, high level, like you can imagine there's quite a few settings in which trajectory data is like kind of reasonable to gather and maybe is like the default way things are actually gathered. So for example, like a person driving, which would be like the policy here from point A to point B, would be like an example of trajectory data, which could then be maybe used for something like self-driving cars. Okay. Now I explain what the assumption, like what the definition of the assumption is. So the assumption looks like this. It says that the offline data consists of n trajectories gathered by some data gathering policy πg. Okay. These trajectories look like this. They're like full trajectories. They're full interactions with the MDP from the start state S1 until the final stage SH. Okay. The importance here is that there is this connection between the next state and kind of yeah, there's this whole connection here. Okay. Yeah, and the way this like gathering looks like is that you would take an action based on the policy πg, which is the gathering policy. You then receive a reward, you get a next state, and then you actually take an action from this next state, and so on and so on. You can think of it, if you try to map it to like the previous version of the data we saw, the important thing here is that this S bar matches SH plus 1. So this next state here is actually matching the start state of the next tuple. Or in other words, you could just think of it as you have samples from the joint distribution that you get by following πg, this gathering policy, from the start state in the MDP. Okay. While before this like general data gathering policy, or sorry, this result of Dillon's before, there was no assumption of like that these next states were connected and that it followed a distribution of any policy. Okay. So there's no questions about that. What we're left with, oh, okay, so just like visually it looks something like this. Like if you had offline data of this form, then trajectory data would actually force your data from the second stage to actually kind of connect with the first stage. And then concentrability for this trajectory data naturally just changes this data gathering distribution μh to be the marginal distribution based on the gathering policy. Okay. So that's all that changes here. And roughly speaking, it just means the policy you're using to gather these trajectories gathers data as well as any other policy. Okay, and so what we end up with is trying to fill in this table here for this question with no extra assumptions on the MDP. Unsurprisingly, it doesn't work. With the linear MDP and the stronger data coverage, of course, it does work. And so we're left with this question mark. And so that was like the point of this work. And so what we did is we answered this positively. So essentially, we said that things work. So with trajectory data and this linear qπ-Realizability assumption, you can get efficient, like sample efficient learning. And maybe one very important word, and okay, so here's the theorem, but a very important part is that what we care about here is like just sample efficiency. No, I'll talk about it in the open promise part, but there's no mention of computational efficiency at all. So the theorem looks something like, under these three assumptions, right, which is linear qπ, trajectory data, and concentrability, our algorithm will output a good policy with high probability using samples that's only polynomial in the quantities of interest. So no dependence on the state space, which I guess is the important part. Okay. So that is kind of like framing the work and what happened. The next whole chunk of the talk will be explaining how this kind of worked. So maybe I stop for a few seconds to see if there's any questions before that.
So perhaps I have a small question.
Yeah.
The concentrability notion is for all policy. It needs to be all policy concentrability. Is this the case?
Yeah. Yeah, you definitely need all policy concentrability for our result to work. I don't even know what it would look like without all policy. Like what would the assumption look like differently here?
Maybe like single policy concentrability, like.
But isn't that something you'd only make in like the policy evaluation setting or something like that?
No, that's common for policy optimization, right? Like it just ends up being like a sort of agnostic style thing where you say like for any pi star, my like suboptimality to pi star depends on like single policy concentrability to pi star.
Yeah, no, I think you're going to need the all policy thing, as we'll see. Yeah, I don't know if it'll work for just pi star. I mean, I definitely don't think it'll work.
Interesting.
Good question. And similar with the qπ-Realizability, like you really do need the realizability of all policies. That
I think makes sense given.
Yeah,
I guess
as an interesting like maybe side note, there's another paper that I didn't mention because it was policy evaluation by Ayush and Zayu or someone else. That showed like trajectory data is not going to work for policy evaluation under qπ-Realizability, but you only have realizability of like the policy you're trying to evaluate, I believe. And I can't remember what concentrability. I can't remember if it was all policy or not. But like yeah, so it's still there's still like I was like partially looking into the question of will policy evaluation work with these assumptions as well, because it is different from the other one. Anyways.
Yeah, that makes sense.
Yeah.
Thanks.
Okay. So shall we get into the algorithm and the analysis? So yeah, so we're going to start with a warm-up. And the warm-up is going to see how things work for linear MDPs. And okay, so we want to define like some learner for this linear MDP setting, which we already know works. So here we don't need trajectory data. Okay, so for this learner, we don't need trajectory data. We just want to see like how it works, and then like can we get something maybe similar? Okay, so I'm going to present one version of the learner is going to be kind of standard, but the analysis is going to be kind of like maybe a little bit weird, and it's actually a little bit suboptimal, but it'll be nice for the future. Okay, so here's what the learner looks like. The learner is like get least squares estimates of some quantity, and this quantity is something that's going to look kind of like the Bellman optimality operator, some kind of estimate of it. Okay, and just for notation, because it's going to keep coming up here, I'm going to use this notation of like q subscript theta to mean the kind of like the inner product between the features and that theta. So this is like the q function based on this parameter. And then I'm going to use v theta to mean the argmax based on the q theta. Okay, so that I don't have to keep writing these inner products and maxes everywhere. So this v theta hat is importantly like the max of q theta at this state. Okay, and then the learner is just going to output the policy that is the argmax of the estimate you get. Okay, so like why is this a good idea? And there's maybe like two high-level arguments for this. It's just like, first of all, why choose these targets? Well, like if this v theta hat was really like something like v star, then you get that you're really estimating something like q star. And then really what's left to argue, so then taking the argmax of q star makes a lot of sense. You basically are you end up with something like pi star. So all that's left really to argue then is that these estimates are tight, or they're good estimates. And it turns out that this linear MDP assumption will allow us to kind of argue this. That is going to say that something targets of this form are really linear. Okay, so how do we see that? Well, we look at the linear MDP assumption. And I just tell you that like this second assumption of saying the transitions are linear can be equivalently written to saying something like, for any function that's a function from states to something like values between 0 and h, there exists some parameter that represents it linearly, well, the expected value of it from some state in action. Okay, so these are kind of like one implies the other of the assumptions. So you can think of linear MDP assumption as stating the following. And with the assumption that the reward is also linear, this implies that objects of this form are also linear functions of the features, which are objects of the form reward plus expected value of a next state function. Okay, and you can see how this looks very, very similar now to kind of what the targets were. So you can see these targets were really samples from something that looks like a distribution with this expected value. Okay, and the f here, like the important thing here, is the f here would be kind of like the parameter that uses this v theta hat as the corresponding function for f. Okay. Okay, so all that is to say is that these estimates are going to be good estimates of objects of this form, which are reward plus next state value. And then roughly speaking, the idea is going to be that since we have like a finite horizon MDP, you can inductively apply this argument over and over again, and only getting like a linear or like a sum of errors over all of the steps in the stage to show something like this, which is you can show something like this, which is that this estimate q of theta hat is going to be a good estimate of q pi star for all stages. Okay. Yeah, for all stages. And this is going to be under any kind of like data gathering or under any policy here. So like at any state in action here. And this is this like extra expectation kind of out here is because we really only have kind of like data coming from some policy. So we can't really guarantee this for any state in action anywhere in the MDP. Okay. But roughly you can just think of this as like saying that the estimates, theta hat, they're like the Q function based on these estimates are going to be good estimates of Q of pi star. Okay, and theirs turns out to be like kind of a guarantee that's fairly easy to show with the linear MDP assumption. And if we get a guarantee like this, then the analysis is actually quite straightforward, and it's going to be kind of like the same analysis we end up actually following for the rest of the talk, and is going to give some kind of motivation for how we do things. Okay, and I do want to note this is not quite the standard way you would do the analysis for the linear MDP setting, and I think you do, well, I'm sure you lose actually an H factor doing this, but it will be quite insightful for how we do things. Okay, so now like all that's left is to really bound the suboptimality, and it's quite easy. The high level idea, or maybe I show one thing, is like, first of all, what is a suboptimality? It's just comparing our policy pi prime, which is greedy with respect to this estimate, q theta hat, compared to v pi star. Okay, so this is just written out as q functions here. And the high level idea is like, okay, if pi prime is approximately greedy with respect to q theta hat, and q theta hat is approximately q pi star, we're essentially greedy with something that looks like q pi star. Okay. And so you do an argument that's kind of like this like policy improvement style argument here. And all you will do is that you can relate this q pi star, and you can change basically this action that's in here to something to match the following action here and recursively apply. So it looks like this. So we can relate this q pi star on the left to q theta hat, because we know q theta hat is a good estimate of q pi star. We then know that pi prime is the optimistic action with respect to this theta hat. Like pi prime is the greedy action. So we can replace pi star with pi prime. And then of course, q theta hat is once again a good estimate of q pi star with that action. Okay, so we get to something that looks like this, where we apply this lemma 2 times. And now we can relate qπ star to qπ prime with the same action. And if we just expand the definitions of a q function, which is that it's equal to the reward plus the following q function, we can get a kind of like a recursive definition like this, which is that the rewards will cancel and we get the same kind of expression here, but for the next stage. And if you repeatedly apply this h times, you end up with a bound that looks something like this. Okay, so you suffer kind of like h times the error you have in estimating pi star, where at each step you're kind of greedy with respect to something that's almost pi star, qπ star. Okay, so this is the rough kind of like analysis you should keep in mind for how things, like how you can get a bound on things, which is like, if we can just guarantee that our estimates are good estimates of q of pi star, then we're essentially done. Okay. So how do we like, now the argument is going to be, how do we kind of do this in the qπ setting, which is our setting. Okay. I have a proof of this lemma, but maybe we don't go over it for the sake of time. Okay. So here's our setting. So our setting is the qπ-realizable setting. And notice that the previous analysis really like hinged on this fact that we had this linear MDP assumption because we needed these targets to be linear, okay, to be able to linearly represent these targets. So, okay, we really want something like a linear MDP, but we have this q-realizable MDP. And here's the argument of like the previous work of Gellert, which is like, why don't we just like transform our qπ-realizable MDP to the linear MDP setting? Okay, this would be great. Then we're kind of done. And so Gellert showed a result kind of like this, which is something like, if you do this process called skipping low range states, and if I guess you came to the last week's RL theory seminar by Zach, then you would notice that this is very similar. So if you skip these low range states, you get a linear MDP. So if you have a qπ-realizable MDP and you skip its low range states, you'll get something that's like a linear MDP. Okay, so I'm going to spend the next slide kind of explaining what the skipping low range stuff and whatever is, so that we can understand what this transformation looks like. And then we're going to somehow try to achieve this. Okay. So I'm going to define this range stuff. So the range is just the maximum difference between a q function between all of its actions. Okay. So take two q functions, and here are these parameters are the parameters for all the policies. Okay, so let me just take a step back. So like every single policy has a corresponding parameter that realizes it. So you can think of q theta pi's as being like a very good approximation of q pi. And here we're just comparing the difference between these q pi's or q theta pi's between all actions. Okay, so in other words, what this tells you is a result as follows, which is like, it doesn't really matter what action you take from a state that has low range, in the sense that take the value function of some policy and then take any other action from that state. You will suffer no more difference in value than the range. And if the range is very, very small, it essentially doesn't matter what action you're taking. Okay, so the high level takeaway is like low range states are states in which it doesn't really matter what action you're going to take, in the sense that it doesn't affect the value of your policy. Okay. So at the end of the day, we're going to want to somehow get an estimate of this range, or like talk about this range. But the problem is this set of parameters that describe all policies is like a very, very big set. Okay. And we're going to somehow want to like approximate the set such that the range is still close to the true range. And this is another result that was shown by Geller, which is it says that, okay, you can get a set of parameters called this G bar, or these parameter vectors. So this G bar is going to be some set that is approximately of size D, in the sense that it contains D parameter vectors, such that if you only compare the Q functions over these D parameter vectors, this is over this G bar here, you get something that is an upper bound on the true range, only scaled by a factor of square root D. So in other words, we can define this like version of range with a G bar to be something called range based on G bar. Okay, so this is going to be like kind of an approximation to the range, but based on a set that contains only D parameter vectors, or approximately D. Okay. This will help because if we ever like want to estimate the set or whatever, you only need to estimate D vectors instead of all the vectors for all policies. Okay, so in other words, if the range based on G bar is small, then those states are kind of unimportant for our value. So skipping those states is not going to cause us to suffer in any way in terms of value at least. Okay. So that's kind of like the first result about this range stuff. The second result is to show that if you skip these states, you're going to get something that's actually a linear MDP in the sense that it's going to satisfy these like linear reward and transition structure of a linear MDP. Okay. So, okay, I guess I have about 15 more minutes to wrap up. So yeah, it's good to know. So yeah, so we come back to this lemma that was shown before, which is that skipping low range states gives something like a linear MDP. And more formally, this theorem or like this lemma is going to look something like this for our purposes, which is this quantity that we really cared about, that linear MDP is guaranteed, which was something like reward plus function plus like next state function is linear. We can get something like that back in this qπ-Realizable setting if we skip correctly, okay? And I'm going to define a bunch of terms here, but like let's just like roughly interpret this quantity here. So we're saying that this quantity on the left, this thing inside the expectation, is a linear function. And that quantity looks very, very similar to the quantity we said would be linear in the linear MDP setting. The only difference here is that there's this extra tau quantity. And maybe I should define what that means. This notation RH to tau is just the sum of rewards from H till tau minus 1. Okay, so this is going to be actually the sum of rewards you get until you stop skipping. And tau is just going to be the stage at which you stop skipping. Okay. So defining some notation here. So we have this trajectory that you sample based on your like data gathering policy. It's just like, so you start at state SH, you take an action and you continue onwards following the policy. So you get this trajectory. This RH to tau notation was just the sum of rewards, this notation. And this tau term is just going to be the stopping stage when starting from SH and skipping according to G bar, right? So G bar gives you some range function. And if you skip according to this range function, which I'll define what skipping according to it means in a second, you're then going to eventually like stop at some state. You're going to stop at some state that has a high enough range. Okay. So more formally, recall that this range G bar is an upper bound on range, the true range. And so we're going to define a skipping mechanism by like the following term, which is like this omega is going to be 1 if the range is smaller than alpha and 0 otherwise. So in some sense, it's going to say skip if the range is small, or sorry, yeah, skip if the range is small. You don't want to include low range states, and don't skip if the range is large. Okay. And so formally, this tau is just going to be exactly the index for which skipping is 1. Skipping is like you skip with probability, or you skip this state, you skip the state until you get to a state where skipping is 0, in which case this 1 minus that skipping probability is 1. Okay, so just maybe rephrase one more time. Tau is going to be the stage at which you stop skipping based on G bar. And the important thing for this lemma to hold is that you are skipping with respect to G bar, which is this like true way of parameterizing your policy space. Okay, so if you knew G bar, then you would get the following lemma above. Okay. So like, yeah, once again, a very important thing is that we're skipping according to G bar here. But of course, the problem that we end up with here is like things will work if we knew G bar, but like, okay, so we're going to look very briefly at how does the analysis look if we knew G bar, but of course we don't actually know G bar. So let's look at how things work if we knew G bar. So it turns out the analysis looks very, very similar actually, or even the learner. So first, let's describe what the learner looks like for this setting. The learner will look almost identical to before, except now the targets will look not like reward plus next state value function. It's going to look like sum of rewards plus next state value function based on theta hat. Okay. So this is really the only difference. And here, crucially, okay, maybe it's the next thing. Okay, so after we have these kind of estimates, we're then going to output pi prime, which is the argmax based on this estimate here. Okay. So the only thing that changes now, we have these different, the targets have changed. And they've changed to exactly those targets that we know are linearly realizable based on the previous lemma. Okay. And the crucial part is to get like these type of targets, to have these type of targets which are linearly realizable, we needed trajectory data here. Okay. So to get these type of targets, trajectories were really required. Without trajectories, I couldn't find of any way to kind of get samples from some distribution that had the same kind of expectation as the thing that's linearly realizable. Okay. And once again, if I just even step back to this lemma, it should be very clear here. It's very important that you're getting a trajectory based on some data gathering policy that this guarantee holds for. So this is the learner. It's almost identical to before. And like, given the fact that we talked about these targets being kind of linearly realizable under the true G bar, right? So if you knew G bar, then we can really quite easily show a very similar result to the previous lemma we saw for the analysis, which is something like, with high probability, G of theta hat is a very good estimate of Q of pi star. But there's this extra caveat, which is not the true pi star we're going to compare to, but it's going to be this pi star G bar, which just skips states according to G bar. So like this pi star G bar just essentially follows pi star. You can think of it as follows pi star for all the states that are high range and follows some arbitrary pi gathering policy for all the states that are low range. Okay. And unsurprisingly, the analysis is going to go as follows, which is to show that skipping these low range states is not going to matter. And then at the high range states, everything looks the same as before. Okay, so if we want to bound the suboptimality, it's going to look something like this, which is we're going to now decompose it into one more extra term, which is instead of comparing pi star to pi prime, we're going to compare pi star first to pi star G bar, and then pi star G bar to pi prime. And the reason why is because it doesn't matter if we introduce pi star G bar, because G bar skips low range states. So this quantity can actually be bounded by something like 2H alpha, and alpha is the threshold we choose for skipping. So since we skip low range states, this is quite small. And then to bound the second quality, you just follow the same process as before, and you get a bound like this. Okay, and that's just using the lemma recursively over and over again. Okay. So if you believe this kind of step, which is like if you knew G bar, then you can really convert your MDP to something that looks like a linear MDP with little loss in accuracy, which is like this 2H alpha, because you really only skip low range states. Then all that's really left is to figure out how we're going to get G bar. So we don't know G bar. Okay. And one thing is that you might just want it like really what you want is a good estimate to this range, which is this range G bar. But it seems quite challenging to actually get a good estimate of this thing because you kind of need to compare like all possible parameters for all policies between all actions. And this might even be harder than solving the original problem. But if you look at the analysis as any good theorist would, and you notice what is like the necessary kind of conditions that need to hold for things to go through, you'll find kind of like the following. Okay, I'm just like, before I say what the conditions are, I just want to mention like one very high level thing, which is like, the important thing to remember is that this G bar is just D parameter vectors. So we can search over the space. Like basically we want to pick some like set that contains G bar, but contains other possible parameters as well. And so we're going to define this kind of set called like bold G of H, which is just going to be a ball that contains D parameter vectors, such that this ball, like each parameter vector is within this ball. Okay. So all that you need to know is that G bar is inside this set, bold G. Okay. And we know G bar only contains approximately D parameter vectors. So we can search for G bar in this set, bold G, by just trying to pick like any arbitrary D parameter vectors and seeing if they satisfy some sort of properties. Okay. Okay. So all that being said is like this bold set G is now going to contain the G bar. Okay, so here are the properties that really need to hold, and I will try to wrap up in 5 minutes here. So here are the conditions. We don't really need G bar, but we're just going to need some G prime, which is in this set G bar. And recall that, in the set bold G, so we just need some G prime that satisfies the following like two properties. The first is that the estimates are good in the sense that they basically satisfy the lemma we wanted. Okay. So this is kind of like obvious from the previous slide. We needed to satisfy this thing, and we know that G bar would satisfy this. And the second thing is we don't want just any G prime that satisfies these good estimates. We also want one that like has high value. So we're going to need some sort of like notion of optimism here, which is we're going to want to pick a G prime that is at least as large in value as the original G bar skipping mechanism. Okay. And this kind of motivates the actual learner we use, which looks something like this, which is, first of all, you want to ensure that the skipping mechanism, the G prime you pick, is at least as large in value as any other G. And in a sense, at least as large as G bar, because G bar is in bold G. So you want to pick a skipping mechanism G prime that is optimistic. Okay, so it's optimistic in terms of value from the start state. And you're going to want it to hold subject to an extra condition, which is that the parameter estimates are good in the sense that they satisfy this inequality, that they're close to pi star G. Okay. So this is like high level idea of like what you want the optimization problem to be. One caveat is like, of course, you don't know what pi star actually is here, but we're just going to like assume we do for like a second here and say like, what would things look like? Well, then you would just pick pi prime to be the kind of the argmax with respect to this parameter. And it turns out that if we do the analysis, the optimization problem condition will like satisfy exactly what we needed in the lemma before, and the analysis of the suboptimality will look almost the same as before, except with one extra like step in there, which is now we have three terms here. And the extra term is this relationship between pi star G bar to pi star G prime. So now we have these three steps. So the first step is the same as we saw in the previous analysis. It's just that skipping low range states by using G bar just gives you this like 2H alpha factor. So it doesn't matter if you skip low range states. The second part, and this is the extra term, is that now our pi prime is going to be greedy with respect to a theta hat that's based on G prime. So we need this term to be related somehow. And it turns out that it's okay to move between G bar and G prime because G prime was optimistically chosen in terms of its value. So here you get this is just based on optimism. And then finally, you end up with this relationship that is ensured to be close to pi star. So once again, the logic here is something like pi prime is greedy with respect to theta hat. And the optimization condition shows that that theta hat is indeed close to pi star of G prime. And so you could repeatedly apply the same kind of process as before of this like approximate policy improvement to get this extra, to bound this quantity. Okay, so that's basically like the whole story here. And all that's left is to kind of address this final issue, which is like, I said this would be really nice to have in the optimization problem, this like condition. But of course, like we don't know pi star of G. So like, how do we actually achieve this kind of thing? Okay, and like, what does it mean for this to hold this expectation bound and whatever to hold with high probability? So it turns out you can replace this whole thing with like some kind of like sample version of what this is. And instead of actually talking about pi star, you can talk about these ellipsoids or sets that contain parameters that you can ensure also contain the parameter that describes pi star of G. Okay, so really, this is what the actual optimization problem in Learner looks like. It's like that condition gets replaced with something like a empirical estimate of it. And instead of using pi star, you use sets of parameters that you're confident will contain the parameter that describes pi star of G bar. Okay. And so that's what the final kind of learner looks like. And to conclude, okay. So the important thing is like, of course, that the actual true pi star is included in this optimization problem. Otherwise, you can't ensure optimism with respect to the thing you actually care about. Okay. And that's possible to show because of this like whole linear MDP reduction business. Okay, so maybe to just like wrap up, like what's next after this work, or like is there any like what's missing? Well, the learner isn't computationally efficient, as you saw by the very ugly optimization problem. So it's not, you can't we don't know how to make it run in polynomial time. So can like the problem be solved computationally efficiently? And if you watched Zach's talk the previous week, there's maybe some hope of like, so he showed something for a very similar setting that is Oracle efficient now. And maybe there's some hope of using like similar techniques for the offline setting, but I haven't like looked into any of that. And the second question is like, is this sample complexity actually optimal? So this is like the sample complexity we got, that it needs to be at least this large, and there's no lower bound. So yeah, the other question is like, is this the best possible? And the thing that I didn't put here, which is like the actual problem I guess I'm partly interested in, is like, will a similar result hold for policy evaluation under the same assumptions? Yeah, so that's everything. Thank you.
Nice.
Great. Thank you, Vlad. Great. Is there any question from the audience?
I can ask one.
Yeah.
Yeah, I guess I was just curious about yeah, this is related to the question before about like say like single policy concentrability versus like all policy concentrability. I guess like the previous paper of like Gellert in like the online setting with linear qπ-Realizability, that one is somehow doing like, you know, it's using this idea of like skipping over states, but it's also doing some kind of like global optimism because you're in like the online setting and you need to explore. I guess like the analogous thing to do here would be to do, yeah, maybe like some kind of like pessimism somehow like on top of this like estimation scheme. But yeah, I don't know if that's really a question. It's just like a thought. Like, I don't know if you've ever thought about that.
I have not, is the short answer. In part because I'm like not like actually that familiar with a lot of these pessimism algorithms. So like, yeah, that's like,
they're like, I mean, they're, you know, they're like the optimism algorithms, except you like flip the sign.
Yeah.
On the bonus.
Yeah. But I guess, I mean, like, I'm just like, yeah, I haven't like looked too deeply into why this is like a good idea in the offline setting.
Yeah, I get you. I mean, like the basic idea, right, is like, you know, if you think about it, like usually like for any algorithm, you know, if you try, say like based on like value function approximation, you know, when you start analyzing it, usually like kind of like two sources of like error will pop up, right? One is kind of like on policy error, and the other is maybe like off policy error, like under the policy that you're trying to compete with. And usually the way what I think about this is like optimism in the online setting, you can control the on policy error. So you do optimism to get rid of like the off policy sort of error term. Whereas like in the offline setting, it's like you're kind of assuming that you can control offline error. And so you do pessimism to get rid of the on policy term because you can't control that.
Yeah, I see. That's interesting. Yeah.
But of course, if you have like all policy concentrability, then you can kind of control both terms in the offline setting.
Yeah.
That was like, I guess a separate point was like, yeah, it is actually interesting to me that you guys are doing some like optimism in this algorithm, even though it's in the offline setting. Like, I don't know if I've seen.
No, I totally agree. I thought about this too. It's like a little bit weird, and I don't have like a super strong intuition to explain like how that happened in the offline setting, or like, yeah, it is very interesting that it happened. That this optimism is needed here.
It is, yeah, it's interesting. Like if you think about, say, like just FQI, like say, imagine you assume Bellman completeness in the offline setting.
Yeah, then you don't need it.
And you just do like, well, yeah, but I guess what I was going to say is like, yeah, if you assume Bellman completeness, then, and you have, you know, all policy concentrability, then like just FQI works.
Yes.
If you're assuming all policy concentrability, then like you could actually do like an optimistic version of FQI, like similar to golf, in the offline setting where you like form a confidence set based on, like square root of element error and then like do optimism over it. And I think that would still work in the offline setting if you have all policy concentrability, but I don't think it would make things like better.
Mm-hmm.
I think it just wouldn't break things.
Yeah.
Yeah.
Yeah. Yeah, because the optimism is now like somehow over these parameterizations of like different MDPs in some way.
Yeah.
And yeah, I don't know. It's a little bit frustrating because like I haven't thought about this project for quite a while, and like I remember I had like a sort of intuition of like how this had related to the online stuff, but now I can't remember it.
Yeah, I get you. No worries. Anyway, I don't want to monopolize the whole time. It's just that one question, so maybe we should see if there's others.
So maybe an alternative could be, instead of the optimism, to see if you can connect the range of G prime with the range of G bar. Do you think there is any hope of doing this, or
Well,
basically it's not possible?
Estimating range of G bar well, which to be completely honest, we didn't really try that hard, or like it was in part like Gellert being like, where is it? Yeah, that this seems like quite hard, and then we just like kind of dropped this idea at the very beginning. But like it does seem quite challenging because like in some sense, like to calculate the range well, you kind of need to like compare all possible actions of all possible policies, and like and it's like you need to compare their value functions. So it's like you almost need to do like policy evaluation for all these policies well, which seems much harder. Like I guess the thing also is that this G prime is not like guaranteeing that the range is actually good for all states. Yeah. No, yeah.
Okay, I think this was my question. Once you move to G prime, you can no longer guarantee that the range under G prime is close to the actual range.
Yeah.
Okay, I see. Thanks.
Oh, by the way, some other random question is just, do you guys actually need like concentrability, or would some kind of like feature coverage assumption work too?
Yeah, this is a good question that we thought about as well. And I don't think we came to any conclusion, to be honest. We did think about it though, like this, yeah, if you just had like some sort of feature coverage with this like covariance, like this covariance, expected covariance matrix being bounded eigenvalue or something, or minimum bound. Because like this works for linear MDPs.
Yeah.
Right? So that's, I guess, where the question's coming from. If you have a bound like that, and I mean, I don't know. There's some part of me feels like it might be okay, but I don't remember.
Yeah. Because it is true that like part of like, a big part of the argument is to show that like things are approximately linear, and like if things are linear, then like if you only need to apply a change of measure to like objects that are like linear, I mean, that's like why you can usually get away with feature coverage. But I don't know if you guys are using the coverage in like some other like intermediate place in order to show that the things are like almost like linear to begin with, right? Like, and maybe like, yeah, so yeah.
Yeah, no. Yeah, I mean, after this work, there was like a list of like a bunch of other things to actually just like quickly check that I never got to, and this was actually one of them. But it was like the other way. It was like to actually just like show that it's not going to be enough, because that was like I think the original intuition I had.
Yeah, that makes sense.
But no,
okay, interesting.
Yeah. Yeah, I really wonder about the policy evaluation result though for this thing.
Yeah, that's an interesting one. I mean, the computational question is also interesting because like there are some cases, I mean, like, especially if you could get something that like just unconditionally efficient, like not even Oracle efficient,
Oh yeah.
Because like the Oracle efficiency thing, like this does give some improvement, but it's like you know, it's a linear setting, right? So like ideally you would like to have something just like unconditionally efficient.
Mhm.
And I guess there are some cases where things are like a little nicer computationally in like the offline setting compared to like the online setting. You know, like one way I kind of think about this is like, you know, in the online setting, like if you have to do optimism, you know, this is kind of like a max problem where you're doing like max over policies and max over value functions simultaneously. And like, you can't really decouple these. Whereas like usually when you're doing pessimism in the offline setting, it becomes more of like a min-max optimization problem where you're doing like, you know, max policy min over value functions. And this is somehow more amenable to using like, say, yeah, I mean like min-max optimization tools to kind of like decouple these things, which is like, you know, that's like an idea that appears in like a lot of these like papers that like Ten Yang did, you know.
Yeah.
But I have no idea how you would even like remotely get started with kind of sort of like combining that technique with like what you guys are doing here, right? Because it's like,
and in those results, I guess he had something. Well, I guess some of them. Well, at least in one of them, I remember he had like stronger concentrability assumptions for things to work, but it was computationally efficient as well.
Oh, are you talking about BVFT? Wait.
Yeah.
Wait, BVFT is not. I would not describe BVFT kind of requires like enumeration over the functions. I don't describe it as computationally efficient.
Okay, maybe
I'm thinking of the more recent stuff, which is mostly making strong. Like the thing about BVFT that's cool is it only requires qπ-Realizability. Whereas I'm thinking of like some of the more recent stuff that makes stronger assumptions like Bellman completeness, but then is trying to get like more efficient algorithms to get like single policy concentrability.
Right.
But like I said, again, like I like the algorithm you're doing right now is not even like doing pessimism, so I don't even know how I would like like yeah, it's not all clear to me how you would like start applying those techniques here.
Yeah.
So
go ahead.
Okay, compared to the online version in Gerhard paper, the algorithm seems already a bit simpler to implement because I don't remember the detail, but I remember that there was maybe in the online version it was necessary to keep a collection of policy that skip a different number of steps or
yeah, there was, I mean, I guess the thing that had to be addressed was like this whole exploration problem of like how do you refine your set of
exactly the refining of G. This part, if I understood correctly, is no longer necessary in the
it's no longer necessary. I guess it shouldn't be that surprising because you already have all the data beforehand, so there's no like exploration that's needed to refine this set, and you already have good coverage. Yeah, no, it's a good question to like exactly like how it differs from the online version. Because like originally we tried to make it actually quite similar, and then we ran into some problems that I can't remember. And then somehow we ended up with something that like I mean we ended up with this, which actually looks quite a bit different. And I don't have a good answer for the relationship of this.
No, okay, but thanks. I think I was missing the fact that yeah, of course you already have all the data, so I guess you cannot refine your G sets.
Yeah, I wish I had a better answer for this.
Okay, I probably have to run right now, but yeah, great talk. I like the work.
Yeah, thank you.
Yep.
Great. Okay. I will stop the recording.